These wind tunnel segments will show the effects of a left crosswind. The model is positioned in the wind tunnel at the heading for a relative wind azimuth of 270 degrees, and the tail rotor is operating at a constant pedal setting. Smoke is used as an airflow visualization device. This sequence shows the tail rotor operating in the normal working state with a crosswind of approximately 5 to 10 knots. The tail rotor is just entering the area of unsteady airflow. Pilot workload in this area will begin to increase as he attempts to compensate for the aerodynamic oscillations. As the wind velocity is increased, the unsteady airflow also increases. With an approximate wind velocity of 10 to 20 knots, the tail rotor vortex rings become visible. Observe that a ring will form and build in size. As the ring increases in size, its strength will weaken, allowing the left crosswind to blow it away from the tail rotor. This dissipating action is evident by diffusion of smoke. It is the formation and shedding of these vortex rings which cause the tail rotor thrust oscillations to occur. Notice that the rings form and dissipate very rapidly and at random intervals. It is this mechanism that produces the high pilot workload associated with flying in this region. Observe the motion of the tail rotor and vertical fin. The model is rigidly mounted, thus the tail boom is shaking. In an actual aircraft, the pilot would see this as a rapid left and right yaw moment. As the left crosswind velocity increases from approximately 20 to 35 knots, the tail rotor moves into the windmill brake state. Notice that as the wind speed increases, the vortex rings will become less apparent and will eventually disappear altogether. Pilot workload in this area will begin to decrease as the left crosswind velocity increases and the airflow through the tail rotor once again becomes smooth. The pilot's major concern in this area would be the weather vaning capabilities of this crosswind. The wind is strong enough to force the aircraft into a left yaw, which the pilot must correct with right pedal. If the application of right pedal causes the aircraft to yaw right to where the relative wind moves into the weather cocking region, the yaw can rapidly progress into a spin. This wind tunnel sequence shows the top view of the OH-58 main rotor disc vortex. The smoke is placed on the edge of the main rotor disc. Notice again that the edge of the vortex is well defined. The model is now positioned with a relative wind azimuth of 330 degrees. An actual aircraft at this point would have a tendency to yaw left into the relative wind. To maintain a constant heading in this position, a pilot would be applying a slight amount of right pedal pressure. The model is now positioned with a relative wind azimuth of 320 degrees, just 10 degrees difference from the previous position. The diffusion of smoke indicates the tail rotor is now operating within the influence of the main rotor disc vortex. It is at this point that a sudden tail rotor thrust reduction will occur. The thrust reduction occurs because of the airflow changes experienced at the tail rotor as the main rotor vortex moves across the tail rotor disc. The pilot must be prepared to apply additional left pedal to prevent the aircraft from yawing right. This sequence shows a side view of the main rotor disc vortex when viewed from the left. It clearly shows the main rotor vortex as it is blown rearward by the wind. As the model is yawed to the right, notice how the main rotor vortex intersects the tail rotor disc. Again, it is this vortex and its turbulence which causes the sudden decrease in tail rotor thrust.